All right, today we're going to talk about something called RC circuits. A circuit containing only resistors and capacitors and possibly EMF sources is called an RC circuit because we have a resistor and a capacitor, or some combination thereof. Consider the simplest possible RC circuit with a capacitance C and a resistance R. The capacitor has charge Q0 on it. It's initially charged. Because it's charged, there's also a potential difference across the capacitor, which we can call delta VC0, or initial, which is the initial charge over the capacitance. And it's illustrated here as having 3 positives and 3 negatives, doesn't really matter which. Once we throw the switch, the charge will start to flow. We'll pretend positive charges flow, and then move out through the resistor, across the switch, which I guess we now say is thrown, so it's like that. And then back to the capacitor, so that some of these positives will start canceling some of these negatives, and the capacitor will discharge. The loop rule says that the voltage drop across the resistor has to be the same as the voltage gain across the capacitor. So delta VR0 has to be delta VC0, but the voltage drop across the resistor is its current times the resistance, and we can then solve over and say the initial current is the initial voltage over the resistor. But that's only the initial current. As the current flows, the capacitor will discharge somewhat. That will lower its potential and then reduce the current. In fact, that will keep happening. Every time the current draws some of the charge off the capacitor, there is less on the capacitor, so there'll be less tendency to push that charge further, so the current will drop. There's a connection between these two, which is telling us that the rate at which the charge is flowing is related to how much charge is actually left. All right, again, we have thrown the switch. Let Q, I, and delta V be the values of the charge, current, and voltage drop at any time. Then Kirchhoff's loop rule still holds, so we still get something like the voltage drop across the capacitor plus the voltage drop across the resistor is 0, or Q over C minus IR is 0. But the current is the rate at which charge passes through the resistor. In a time dt, we'd have charge dq pass through the resistor, such that dq is I dt. But all of that charge must come from the capacitor. So every bit of charge showing up in the resistor to pass through has come from the capacitor at some point. So it's reducing the charge q by the same amount. In other words, d little q is minus d big Q, or, and this is the important bit for all of this, the current is also related to dq dt, where big Q here is the charge on the capacitor, and the rate at which that changes is the current, with a minus sign to account for the fact that positive current flowing out is a decrease in charge on the capacitor. So we can take our original equation and we can substitute that in, and we get the minus, we get Q over C plus dq dt R equals 0, and then we can rearrange this to get that the change in the charge on the capacitor over the capacitor is negative the change in time over RC. Right? Because remember, again, this is negative, but this thing has to be positive, so the negative sign takes care of it. A little bit of warning, not too much to be worried about, but we're about to do some calculus. And if you haven't done this in your math class yet, then you can just let this kind of slide by, or you can see this as a preview of stuff you'll be doing at some point. We do an integral on both sides. The integral of dq over q, which is like a dx over x, is the natural log of q. And realistically, I should probably put absolute value bars here. I got to drop them. We know the charge is positive. We said it was charged on the positive capacitor, so I don't have to worry about taking log of a negative here. But your math teachers would probably be happier if you did that. And then the integral of minus dt over RC, well, RC is a constant, so I can pull out front. So if minus 1 over RC, integral dt, that's easy. That's just t. But then we have plus some arbitrary constant. And again, your math teachers are probably going to teach you to do it with a plus, that the integral of like dx is x plus c, where that's your arbitrary constant. Obviously, c is bad news for us because we already have one. So I'm going to pick k. And then I'm going to say, instead of saying k, I'm going to add the log of k. Well, if k is an arbitrary constant, then the log of that is also an arbitrary constant. So I have made the calculus gods happy. And so I'm okay with this. I do, on the other hand, have q locked up inside this natural log, which is frustrating. So I have to liberate it, and I do that by exponentiation. So I say e to the log q. And I do that because e to the log q is going to give me q. But if I do it on one side, I have to do it on the other. So I also have e to the whole thing. This whole thing is all being exponentiated, e to the minus t over RC plus log k. Now we know that when we exponentiate a sum, it becomes the product, so we now have e to the minus t over RC times e to the log k. But of course, e to the log k is just k. That was the reason for doing it in the first place, is to get my universal constant, my arbitrary constant, out front instead of having it trapped inside some weird e to the some things. It doesn't matter much, it makes life easier. All right, we know that we start that q0. We start with q is equal to q0 when the time is 0. So I put that in. I put q equals q0 equals k e to the minus 0 over r. Oops, this should be over RC. Sorry about that. Equals k e to the 0 equals k, telling us ultimately that our arbitrary constant is actually just the initial charge. And then we get the very important result that the actual charge as a function of time is the initial charge times some exponential decay, and the exponential decay is being controlled by this product RC. We traditionally write our thing, which is q equals q0 e to the minus t over RC. We often write it as q0 e to the minus t over tau, where tau is this thing called the time constant, and it's equal to r times c. Tau is a characteristic time for the charge to bleed off, which is a phrase every textbook uses, often without defining very well. We do know that a large tau means the circuit will take a long time to discharge, and a small tau means that it will take less time. Notice that a long time to discharge can come from having either a large R, because the current won't flow very well, so the charge will leave only sluggishly, so it takes a long time for it to go, or a large C, where we just basically have a lot of charge we can get rid of. So, because remember that the original charge is proportional to the voltage times that. And so having a large capacitance means that it's easier for the charges to stay on the capacitor. They don't want to flow around, so the current is also sluggish. So either R or C slows things down. We see from this that the capacitor discharges exponentially along this curve, an e to the minus x curve. And this comes back to how we said that the current was proportional to the charge, which means the rate at which the charge changed was proportional to itself. And the exponential is the curve whose derivative is proportional to itself, whose change is proportional to the value of the thing itself. We also know the voltage and current are proportional to charge because V equals Q over C and I equals V over R. And so we get that they have the same exponential decay with the same time constant, that they all fall off according to this picture. Be careful, the time constant is not the time it takes the capacitor to discharge. We would have called it the discharge time then. In the model we have here, the capacitor never actually fully discharges. It just gets infinitesimally close to it. Rather, tau is telling you how long it takes to fall to 1 over e of the original value, or to about 37% of its original value, or in really rough terms, to about 1/3 of its original value, a little bit more. Traditionally, engineers will say a capacitor is considered discharged after 5 tau have passed. At that time, the capacitor would hold less than 1% of its original charge. All right, consider two circuits with capacitors fully charged. In circuit P, there are two capacitors arranged in parallel. In circuit C, there are two capacitors arranged in series. All of the capacitors here are identical. If these circuits are used to light bulbs during discharge, which bulb stays lit longer? We are clearly looking for the larger tau, which is RC. The R is just whatever's in the wires and is therefore essentially constant. So we're looking for the largest C. And we can see that when we have things in parallel, they just add. So this becomes, if this is C and this is C, this becomes 2C. Whereas things in series becomes 1/2 C. So in the parallel case, the time constant is longer, and so the bulb will take longer to discharge. Let's see if that analysis was correct.
Demonstration, I have two circuits. Both have identical batteries, 6 volts. Both have identical light bulbs, and both have two capacitors in each. The top circuit, the capacitors are in parallel. With the bottom circuit, the capacitors are in series. Now if I move these switches, this will charge both capacitors at the same time. The question is, when I discharge the capacitors into the light bulbs, what will happen? Will the light bulb in the parallel circuit light longer? Will the light bulb in the series circuit light longer? or will they both be lit for the same amount of time? As you can see, the light bulb in the series case went out quite quickly, and the light bulb in the parallel case is still lit and will be for a few seconds more. This is because capacitors in parallel add together, so the equivalent capacitance in the circuit is 2, and in the series case, capacitors add, the reciprocals add, so the equivalent capacitance is really 1/2. So therefore, the light bulb with the in the series was lit for a much shorter time than that in the parallel case.
All right, this capacitor is initially uncharged. Immediately after the switch closes, the capacitor voltage is which of these values? Well, immediately after the switch closes, there's no time. The current here is like, or the charge here is like, oh, I really want to go, I want to pick up charge, but it takes time for charge to move from the battery to the capacitor. So immediately after, there is no voltage across the capacitor. It is uncharged, and V equals Q over C. We can also, of course, charge capacitors, otherwise they'd be kind of useless. So consider this circuit where we now have a switch. There's an EMF source and a resistor and a capacitor, but we've broken the circuit with this switch. And we'll say that at t equals 0, there's no charge in the capacitor. When we throw the switch at t equals 0, the voltage across the resistor must equal the EMF. We do a Kirchhoff's loop around this, and we say whatever we gain in EMF, we lose here and we lose here, or maybe gain here, but this is 0. And so all of this EMF has to be lost going across the resistance. So the initial current is EMF over R. As the current flows, the charge builds on the capacitor, which means that this side becomes positive, and that means that it's tending to push electrons or push positive charges back this way. It's resisting, I should say that, it's pushing back against the EMF, and so less current, because now it's less easy for a positive charge to go this way. The battery is probably still going to win, at least at first, but as more charge moves through here, as the battery wins, and we build up more charge on the capacitor, we'll end up getting that we can't get much flow anymore, that the charge that has flowed out has created positive charges here that are trying to move back this way, right? As new positive charge comes in, they push back, and so the current drops. In fact, we again have the amount of current is going to drop as much as the charge on the capacitor is changing. Therefore, we should not be surprised at all that we're going to get an exponential growth in the charge as well. A similar but somewhat grungier analysis by calculus would show that the charge, voltage, and current obey the following things: that the current is still the initial current times an exponential decay, but both the charge and the potential grow, so they have a 1 minus the exponential decay, and it's either EMF or C times the EMF as they grow exponentially. And again, never really quite reach their maximum values, get exponentially closer to them as time goes on. All right, what resistor in ohms would be needed so the 6 microfarad capacitor would have a time constant of 3 seconds? Tau is RC, so R is tau over C. So we have 3 seconds over 6 times 10 to the minus 6 seconds, which is 1/2 times 10 to the minus 6, 10 to the plus 6 ohm, which should be 500 kilo ohms. Oops, that's terrible. All right, the red curve shows how the capacitor charges after the switch is closed at t equals 0. Which curve shows the capacitor charging if the value of the resistor is reduced? So we want to think about this. We're talking about the charge on the capacitor, and at the end of the game, the capacitor is, of course, going to have the same voltage as the battery, which means it's going to have the same charge no matter what this resistor is, because the charge is going to be EMF over C. So whatever we have should be the same. Our thing should be heading to the same place as the original curve. So if the red curve is the original curve, then the only one that's properly approaching it is B. I guess conceivably it could also have been C, but a long time, right? Oh, and then we've reduced the resistor, so we've reduced tau, so we should be getting there faster. So while both B and C are converging towards this red curve, C is taking too long.